Good afternoon, everybody. We are starting our session on advances in InSAR theory and methodological innovations. Well, we have 5 very fine papers to hear, and so I would rather start immediately with the very first. That's the one to be presented by Howard Zipker. And however, Howard is not really here because it's still too early in California. So I will present the paper for him, but he will join us later on because he's going to chair the next session. So if you have questions for him, well, I'll try to answer if he can, and then soon enough, you'll be able to talk with him when he joins us. So let me start with the very first presentation. And okay. And this is a signal model for PRF dithering in wide swath fine resolution InSAR. And let me first try to explain what PRF dithering is meaning, because basically what we want to talk about is just getting rid of some of the pulse that we emit for doing something else. And then we will be left without pulses, but then what we still get is still enough to have nice and interesting interferometrical pictures. So the real goal of this presentation is that wide swath imaging produces echoes lasting longer than the interpulse time. And then many systems overcome by segmenting the swath, could be ScanSAR, could be TOPS. In other words, you are allotting antenna time to watch one swath or another swath. Here, we are thinking of doing another thing. That is, looking at all the swaths, pulse by pulse, changing them whenever we want, and then ending up with a very random acquisition, but at the same time, maybe multi-swath. So we can produce, we examine the effect of subsampling in azimuth rather than in range. So we steal pulses, and we use these pulses to illuminate other echoes. Howard derived a model of the noise introduced by this dithering, and then examine the InSAR product that we will see are extremely robust to this pulse stealing. Okay, wide swath. This is a satellite, illuminates the terrain, and basically it's just the antenna that tells what is the beginning of the swath and the ending of the swath. There is a center beam, and then the antenna width illuminates a rather wide swath on the terrain. And this is, in general, higher than the interpulse. In other words, if we look at the pulses as they are generated by the pulse repetition frequency, this is the time interval, but then the received power is really much longer than that, so that really we have the well-known range ambiguities. When we are seeing one effect of the pulse, we also, at the end of the swath, and we are observing, we see arriving the next pulse, and so on and so on. So you see that basically there is, on one side, the necessity of extending the interval between the pulses to accommodate all this. At the same time, if we extend that too much, we know the satellite is moving, and then we start aliasing in space, and we get the azimuth ambiguities. So this is a problem that we have all the time. How to solve the problem? This is a proposal by Howard Zipker. Let's come to that. This is a key slide of the talk. So really, I'll spend some time to explain this slide. What is this? This is a satellite that's illuminating. This is a ground swath, 300 kilometers, 3 swaths, one next to the other. So here, suppose that we have an unlimited PRF. So we have very many pulses being emitted. So basically what you can do is illuminate the first swath, then the second swath, the third swath, and again the first, again the second, again the third. So basically you can think of a continuous illumination of 3 swaths, provided you have a very high repetition frequency. But you don't have that, because basically it's not possible to have such a high repetition frequency and at the same time to be able to observe everything. So we need to do something else. And this is what Howard is proposing. So you just illuminate with your satellite this part of the swath, and with the next pulse you illuminate that part of the swath, and then this one, and then this one, and then this one, randomly. So basically, successive pulses illuminate at random the whole set of three swaths. What you end up having? Well, 1/3 of the pulses on any swath, because basically the other 2/3 are devoted to the other swath. But then you have randomly in time, so you have a Poisson sequence of pulses, and at the same time, you have illumination of all the three swaths. Or if you are more modest, you can reduce the number of pulses, not as much as from 2/3 to 1/3, but you can reduce less and then basically only extend the interval between the pulses. So this is what Howard calls dithering. That is, we are getting rid of some pulses using some illuminating other swath. And so you can have a regular subsampling, randomized subsampling. Regular subsampling means doing it systematically. Randomizer means doing with a given probability. Then there is a noise is being developed, and then we will show example that shows the robustness of this result with respect to what we are getting. So this is a full window observation. Then if you have a cosine modulation, you get, this is one, the Fourier transform spectrum actually of the original window. This is a classical sign, cardinal sign. Then you have the modulation, and so we have peaks because we have the two pikes of the cosine in the frequency domain. Then with a square wave, you see a different thing. For regular impulse, you see and with random pulses, you see the autocorrelation function, and you see a big spike and like noise. That noise basically is due to the randomness of the sequence of the pulse. But still, you see, comparing this and that, you see that as long as you have enough pulses, then the noise corresponding to the randomness is not so relevant. And so basically you see that getting rid of pulses is like increasing this noise with respect to the peak of the autocorrelation, similarly to what happens with the different signal-to-noise ratio. But let's look at the number. If you are dropping 20% of the pulse, this is equivalent to a signal-to-noise ratio of -30, -40 dB. So really you see that dropping 20% of the pulse corresponds to noise, but not too much. So basically the same thing as you would have with the signal-to-noise ratio between the peak and the, this is noise, but the peak and the total noise of 5 dB. So it means that we still have a good coherence, because if we have a power of 3 between the signal and the noise, then the coherence will be quite nice. So noise increases as pulses are dropped. Then we can also do another thing. We can interpolate. If we miss a pulse, then we can use a previous and the following line, and we interpolate. Lower frequencies will be set. Higher frequencies will be in a different situation. So will be lost. But anyway, we can improve if we have oversampling. If we have some oversampling, then we can recover the lost pulse. So you see now a picture that tells you how to estimate the effect of this oversampling. And this is lower frequencies up to 1/2 of the Doppler are adequately estimated, because basically we are supposing not to miss more than 50% of the pulse. So the lower frequencies are well estimated because they can be well interpolated. The higher frequencies will be undersampled and misestimated. So we can kind of estimate the signal-to-noise ratio we are getting out of this randomness of the pulses being thrown away or used to extend the interpulse interval. So you see that the different signal, that is a signal corresponding to the existing pulse, is fully operating. The noise, this part here is not seen, is kind of aliased. And so basically this part is not seen. If we have all the pulses, then we would have the complete bandwidth from 0 to the full bandwidth of the azimuth bandwidth of the signal. So missing samples will be able to sample well here and not so well here. So we have noise. How to calculate the noise? This is a key equation, and really I want to have Howard explaining this very well, but we don't have much time to explain that picture. But basically, it's a very simple method of estimating the signal-to-noise ratio, computing the part of the well-covered signal, the part of the non-well-covered signal times the pulses you have, and then you estimate the signal-to-noise ratio, and then you have an oversample that allows you to interpolate, and eventually you get a simulation of the noise. So the equivalent signal-to-noise artifact for the listening losses. You are missing pulses, how many? 10%, 20%. The equivalent signal-to-noise ratio will be 5, 6, 7 dB. So you see that we are not missing much in terms of signal-to-noise ratio, even if we are missing 20% of the pulses. This is the key point of the presentation. And so let's see now the effects. So do examples processing ALOS data for a study, the formation of Kilauea, the geocoded SLC single loop complex will be calculated using just back protection on the ground. The interferograms will be obtained, the correlation images, and we'll see what happens if we are missing pulses. And you see the case of a forest, no pulses, 20%, 40%, you don't see it. Because on a forest, certainly it's hard to see. Maybe you could see something here, but really not much. Interferograms, really you see nothing. And so even with 40% of the pulse being dropped, you just see no change. And the correlation, similarly, with the 40% of the pulse dropped, you still see that the covariance is still very well estimated. Interferograms. With interferograms, you look at the quality of the fringes with 40% of the pulses. It's okay. It's so really we are not missing much on the interferogram. Certainly, on the image, you would see it. So no question that the noise would be there. But if you correlate the image with itself, because that's what it is an interferogram, then you see that you are not missing much. And this is the key point. The correlation is good, even with 40% of the pulse drop. And the time series deformation, we now know that the phases are so robust with respect to the signal-to-noise ratio that we expect that even dropping pulses, we won't get big differences. You see that 0 dither, 40% dither, you see that basically the points are superposed and there is no big difference in the change. So the conclusion is that InSAR is robust with respect to missing pulses. Future nicer products will be produced, so we can tolerate quite a number of dot pulses. Then this means that we could improve the coverage at the expense of the loss of SNR. So in other words, we have a possibility of trading SNR and coverage. Actually, if you can go another way and you compute the coherence of the, then it's very easy to find that the coherence loss due to a P probability of pulses is square root of P. So with 30% of the pulses, so really that you could cover 3 swaths, you would have a coherence loss just due to this of 60%. So it's 0.6 is not so bad anyway. So this is basically the talk, and I am back to the presentation. I'm stop sharing. Right. And so now I move to the next presentation. And the next presentation is going to be the one by Homa Ansari, and she will be talking about observation of fading signals in multi-looked interferograms and deformation velocity maps. So this is a very important topic, and other authors will discuss this point. So please, Homa, be clear and explain this story, because really we understand that using this methodology, we can watch the grass grow. Go ahead.
Sure. Thank you, Professor Roca. Yeah. Unfortunately, I received an echo. Now it's gone. So good afternoon, everybody. My name is Homa Ansari. I'm from the German Aerospace Center. And as Professor Roca mentioned, I would like to introduce a rather new concept in SAR interferometry, which we call fading signal. And this is a work together with Francesco De Zan and Alessandro Parizzi. Let's start by showing you 3 different deformation maps from distributed scatter interferometry schemes. These deformation maps are from Sicily, Italy, and they show completely different signals. But you will be surprised if I tell you that the only difference among the 3 different processing schemes is that we are choosing different subsets of interferograms in order to retrieve the deformation. This observation raises two questions for us. The first question is, which of these deformation maps is correct anyways? For this, we need accuracy assessment of distributed scatter scheme in general, and this would be the first question that I would try to address here. The second question is, where does this discrepancy come from? What is the source of this discrepancy? And this is where the idea of fading signal comes into play. Let's start by answering the first question. For accuracy assessment of distributed scatters, we would resort to the persistent scatter interferometry. The reason is that persistent scatter interferometry, or in short PSI, is an established method, and its accuracy as well as the precision has been thoroughly scrutinized by the InSAR community previously. So in this accuracy assessment, as I mentioned, I go back to Statistical, the same deformation site that I just showed it to you. We use Sentinel-1A and B images, a time series of images of 184 SLCs to be exact, spanned over 4 years of data. And once we completely take the persistent scatters as our benchmark and perform a deformation analysis and keep this as a benchmark for our performance analysis. Then we move forward to distributed scatters, and these are multi-looked interferograms, so to say. And from the multi-looked interferograms, we retrieve the deformation. Then we start with the first scheme in distributed scatters, where we are using only short temporal baseline interferograms, or in short, the SPAS method. And we only use 5 consecutive interferogram per SAR acquisition. This means that we would have a temporal baseline limitation of 40 days. In a second scheme, we increase this temporal baseline to roughly 78 days of temporal baseline, and using 10 consecutive interferograms for the deformation analysis. And to go to the extreme, we use all the possible interferometric pairs in a phase estimation approach. This is the idea of phase linking. And here specifically, we use an efficient phase estimation, which we proposed before in this paper that I cite here. So now what I do is that I would retrieve the deformation signal from these 3 DSI techniques, and I compare it with the PSI benchmark. And here is the result. So basically what I'm showing here is from left to right, the spatial difference of the persistent scatters with respect to the multi-loop distributed scatters when I'm only considering 5 consecutive interferograms per SAR acquisition, increasing it to 10, and further increasing it to the entire or the full exploitation of the time series, so to say. What we see is that on average, there is a bias in the deformation estimation. And this bias is much more pronounced for shorter temporal baseline interferograms. This bias for the SPAS 5 or the 5 consecutive interferograms is 6 millimeter per year. While increasing the temporal baseline, we achieve 3 millimeter per year, and using the ME, we achieve to sub-millimeter per year accuracy of the deformation. The same trend happens for dispersion, but with dispersion, it is statistically completely expected that if we use more interferograms and they are of the same quality, we should see a decrease in the dispersion. What is odd for us with the classic interferometry that we all know about is this bias, and where does this come from? So this brings me to the second part of the talk. Where is this bias coming from? And we would argue that this is from an overlooked phase component in the multi-looked interferograms. Let's go back really to the basics of InSAR. For this audience, I should not introduce that there are different phase components in the interferograms. Very well known are the atmospheric phase component and deformation phase component. Also, the changes in the scattering behavior. These are very well known. When it comes to changes of the scattering behavior, specifically for the distributed scatters, it is very well known for this audience that we would see a decorrelation noise as a result of this scattering change if it is completely stochastic. What is less known, however, is that such changes in scattering behaviors can also introduce systematic signals. And these systematic signals are very much in line with the idea of phase inconsistencies among different Intel programs and the idea of phase misclosures, which is the work of my colleague Francesco De Zon, and you can refer to this paper for this. Now, to go further, I should mention one more fact that for persistent scatters, we are choosing persistent scatters, first of all, such that such changes in the scattering behavior is pretty negligible, which means that such concerns, being it systematic or stochastic, is not a concern for persistent scatters, but rather for multi-loop interprograms and for distributed scatters. That being said, we argue that this systematic signal is in place for introducing deformation velocity biases, and we would like to prove this hypothesis here. For that, we resort to the following. We try to reveal the systematic behavior in the changes of the scattering phase. And how we do that? We propose the calculation of residual phase screens. These residual phase screens are basically the discrepancy between the phase of the persistent scatters, which are single look, with respect to the phase of the distributed scatters within a very small estimation window of 140 meters. If we are taking this small estimation window, and if we suppose that the deformation and atmospheric signal are stationary within this window, which is not a hard assumption to meet, then what we are left of when we calculate this residual phase is actually the scattering, the changes in the scattering behavior. So further, in order to show whether these changes in the scattering behavior is systematic or is stochastic, what we would do is that we actually perform an averaging of the residual phase screens uh, um, over a temporal baseline. So in such a fashion that we take a temporal separation of the interprograms, and we calculate the average of these residual phase screens over over the interprograms, which more or less share the same temporal baseline, and we call these lag K interprograms. Furthermore, we also have a normalization with respect to the temporal baseline, which is our next objective of propagating this error, but this is of minor importance at this stage. So let's have a look at what happens to the Sicily Calabria. Here is the residual phase screen versus temporal baseline. On the left-hand side, you see the residual phase screen for lag 1 interprograms. And what we see is a very pronounced signal over these vegetated areas, for example. Whilst when we are going to lag 10 interprograms, this signal is disappearing. The same trend can be shown with the PDFs and with the showing of the mode of this PDF with respect to the temporal baseline. As we see, with the increase of the temporal baseline, this phase component is fading away, hence the name fading signal. If we don't take into consideration that temporal baseline normalization, we still see the same trend or same behavior of fading of this phase component over temporal baseline. Now, if we propagate this error, we can actually predict the expected error that we can see out of SPAS techniques. For example, for SPAS 5 and SPAS 10, what we do is that we integrate the residual phase screen for lag 5, up to lag 5 and lag 10 respectively, in order to retrieve the expected deformation bias. And having this PDF of the cumulative error of the predicted error, we can see that we expect 5 millimeter per year and 3 millimeter per year for SPAS 5 and SPAS 10 respectively. Going back and comparing these numbers, which are from the predicted velocity bias and are the result of the revealed residual phase screens, and comparing them to the empirical deformation error that we had in the first chapter of the talk with the accuracy assessment with respect to PSI, we see a very nice agreement between these two results. This for us shows that the fading signal is actually explaining the observed deformation bias. This was one observation over Sicily, Italy. We have further observation over more arid climates, for instance, in this case, over Tibetan Plateau. And here we basically see the same observation with a difference in the sign of the bias and of the phase component. This brought us to the idea that there are different physical phenomena and physical models that can explain this phase component. There are two postulations of two physical models by my colleague, one related to moisture variation and the other to vegetation growth that you see in these two works. So with this, I would like to summarize this talk and also, if I may, provide some recommendations for the InSAR community. In short, I try to show it to you that there is a physical signal in observed multi-looked interferograms, and it fades away with the temporal baseline, hence the name fading signal. Ignoring this signal compromises the accuracy of the formation product. Its mitigation is possible if we are using long time series and if we are actually exploiting the longer temporal baseline interferograms. And maybe my one takeaway message from this talk would be that that the short temporal baselines are pretty dangerous, specifically for deformation velocity estimation. This should be avoided, although they are more coherent, but they are more susceptible to the fading signal. And the second takeaway message is that the big data processing schemes can compromise mission capabilities. This we try to show for Sentinel-1. We believe it will be the same case for NISAR in the future. Our recommendation further for the InSAR community and for space agencies specifically is that we could actually design analysis-ready InSAR products based on the efficient and high precision phase estimation approaches, such that the user does not have to really deal with this problem of which subset of interferograms to choose or how to go about the choice of these interferograms. This can be taken care of by the big data processing approaches. And in order to improve the computational efficiency here, we have and allow for real-time processing, we have our proposal of sequential estimator in this case. One of my maybe finalizing points is regarding the residual phase screens that I try to introduce. I find these a very rich source of information and very rich features for detection and analysis of the fading signal. Here I would like to show you that, for example, on the left-hand side of this slide, over Sicily, Italy, and using these residual phase screens as features, I have performed a machine learning clustering approach in order to detect the fading signal and in order to actually choose which of the areas are prone to the fading signal and which are of the distributed scatters are actually less prone and more resilient toward the fading signal. And on the right-hand side, what I show you here is the quantification of the associated error that comes to fading signal. And this can be, again, achieved from the residual phase screens through the propagation of the error and a priori to performing any kind of...
2 minutes.
Yes, sure. A priori to performing any processing at all. This was the final part of my talk. Thank you so much for your attendance, and I'm very much looking forward to questions and discussions afterwards.
Thank you. Thank you. And now I would like to tell everybody that for questions, you have the Slido tool on so that you can really write your questions on on your screen and then add an to add the name of the author to whom you are addressing your questions. And then all the questions will be discussed at the end of this session so that they will be discussed together. So please write your question on the Slido tool, adding the and the name of the author to whom you are addressing the question. And now, so let's move to the next talk. And the next talk is closure phase and systematic bias in multi-looked SAR interferometry, but it's going to be presented by Jujie Zheng. And so the screen is yours.
Sorry for the delay. I forgot to unmute myself before I start. Hi, everyone. So my name is Yu Jie, and I'm a postdoc at Caltech. My co-authors include Teresh, Piyush, and Mark Simons. In this talk, we would like to further discuss the relationship between closure phase and the observed bias in multi-looking SAR interferometry. Closure phase measures the phase consistency among 3 measurements. In InSAR time series, we typically decompose InSAR measurements as the difference between phase history at 2 different times. And by this decomposition, the closure phase is always 0. Therefore, phase closure is an intrinsic assumption in InSAR time series. However, this is not the case in observation. There have long been discussions on systematic closure phase errors. And as just highlighted by the great talk by Homa just now there are observations of systematic bias in time series as well, especially in short temporal span subsets. In this talk, we aim to answer this question: what links closure phase errors and the observed bias in time series? And we would like to present a model that can consistently explain both the observed closure phase errors and the observed bias in time series. Since closure phase errors only occurs in multi-looked interferograms, naturally, we start by investigating the role of multi-looking in closure phase errors. Multi-looking is essentially just spatially averaging. If the measurements are homogeneous, the multi-look phase is the maximum likelihood estimate of the true phase. In this case, by multi-look processing, we are collapsing in this example, 16 measurements into a single measurement that reflects the true underlying signal. However, when the measurements are no longer homogeneous, for example, if there are 2 different underlying signals, then the multi-look phase is a function of phase 1, phase 2, and the amplitude ratio between these 2 signals. When the phase difference is small, the multi-look phase can be simplified as a linear combination of these 2 phases. The coefficient is a function of the amplitude ratio R. For example, if we have both deformation and some local process that I denote with X going on in the same multi-look window, then the multi-look phase is not only deformation, but also a weighted version of the process X. And the coefficient is, again, a function of the amplitude ratio R. And we know that interferometric amplitudes are proportional to correlation, and therefore, with increasing time span, if we can see if correlation drops and then WR decreases with time. Therefore, the presence of this local process X will look like a fading signal that decays with time. This is essentially our model, and with this formulation, we can also explain closure phase errors. We can write interferometric phase into 2 parts: first deformation, and then a weighted version of this local process with a weight of the W delta T. Delta T is the time span between acquisition 1 and 2. Similarly, we can decompose delta phi 2-3 and delta phi 1-3. The resulting closure phase is not 0 because the weights for the delta T, which I'll call connection 1 interferograms, and 2 delta T, which I'll call connection 2 interferograms, are different. And the closure phase is in fact only sensitive to this process X. And if we write out the subsequent closure phases and sum them up, we can actually get a version of the phase history of this local process X. And we can also expand the definition of closure phase. Instead of connecting the loop between 3 acquisitions, we can create a loop of 4, 5, or even more. And the resulting cumulative closure phases are all proportional to the phase history of this process X, but with different weights. Assuming the weights decaying with time and is negligible at P connections, then we will be able to solve the bias for connection 1 interferograms. And with that, we can solve for the bias for connection 2, 3, and up to P connection interferograms. With the estimation of the weighted phase history, we can then move on to predict bias for limited bandwidth analysis. And now I'm going to show you an example of as regular SBAS. So as contrast to the previous talk, which used, I think, more like a squeezer approach. So this is using SBAS processed by MinPy, but also with different bandwidths, which means there are subsets with different at maximum temporal baselines. And the area is in Central California, which is a very arid area, and as shown on the right plot, there are some dry lake beds and also agricultural areas near the Colorado River. And as you can see, we also observe this different velocity maps, especially in the left plot, where you see much more velocity patterns than the other two. To validate our model, we sum sequential closure phase to estimate the cumulative bias in the time series. First, let's look at the triplets. This is an example of a closure phase formed from using the acquisitions from 2017 February the 3rd to 2017 May the 10th. And then we have the next one and so on. And if we add these up, we obtain a weighted version of the cumulative bias in our time series with a weight. And the same can be done in other connection level closure phases. For example, these are connection 20 closure phases. The sum of these closure phases gives us another weighted version of the cumulative bias. As you can see, the cumulative bias in the bottom is has much more visible pattern than the top one. This is because the weight of this longer connections cumulative closure phases is bigger. Specifically, if we assume that the weight of this process X signal has become negligible at 20 connection levels, then this map will actually give us the velocity bias for a bandwidth 1 time series analysis. So here is if we apply this method to estimate the bias for the previous 3 velocity maps, and the bottom row is the estimated bias. And this is the corrected time series. And we can see the previous signal in bandwidth 1 has been successfully removed, and all 3 bandwidths are more or less consistent with each other. And we can also zoom in to a smaller part, which is dry lake here. And again, we can see the bandwidths 1, 5, 10, and before and after correction. As a comparison, I also included another velocity maps using full bandwidths processed by the software FRINGE, which adopts a squeezer approach. And we can also look at 1 point, the time series. And this point is marked by this black star. It shows the estimated bias, the before and after corrections. And once again, we see the uplift signal in the bandwidth 1 is successfully removed. And here's another example over a different area. This is an agricultural area. We observe this sort of a fading blue signal in the top row. And after correction, the blue signal, which is subsidence signal, is removed. And here is another closer look at one of the points. And just to show you before and after corrections. Finally, we can also estimate how long the local signal remain correlated. In these 6 plots, 1 means they're correlated and 0 means the signal has gone. And we can see that it's most of the signals that we're observing are gone after roughly 60 days, and different areas has different decaying speed. Yeah, and here's my summary. Local processes with decaying average correlation inside multi-looking window leads to both systematic bias and closure phase errors. And we can correct these bias with cumulative sequential closure phases. And if the average temporal baseline, which is the delta T bar, is longer than the lifespan, which is tau, of the local process X, then the bias is negligible in time series analysis. And that is all. Thank you.
Thank you, thank you. And so now we have 2 minutes. So maybe you could, I have a question that I have the same for Uma. Do you think that you can make 2 products, one for the fading and one for the long term? That's what you are advocating, because basically you are extracting the fading part.
What I was actually advocating was one single product where the effect of the fading signal is eliminated. But then if we have this product in place, the retrieval of the fading signal product would be just a derivative, no? I mean, it would just be the difference between the the direct interferograms and the product that we have in place. Because we are just basically talking about one phase component.
Thank you.
Sure.
So now we are moving to the next talk, and the next talk will be machine learning and data fusion for InSAR over distributed scatterers, and to be presented by Philip Conroy. So Philip, please go ahead. Unmute.
Sorry. I forgot to unmute myself. Yeah. So thank you, Professor Roca. My name's Philip, and I'm going to be discussing 2 applications of machine learning for InSAR over distributed scatterers. This work is part of a larger project called Living on Soft Soils, and we are seeking to understand subsidence in the Netherlands across multiple scientific domains, and InSAR is one key to that equation. So to give you an idea of what it is we're looking at, you can see this scene on the right-hand side. This is a very typical Dutch pastoral scene. And most of the sort of agricultural land in the Netherlands looks like this. It's composed of peat and clay. And we understand that this is slowly sinking over time, but it's very difficult to get sort of hard data because it's extremely difficult to actually directly image or use basically InSAR over these areas. And for now, we've had to make do with persistent scatterers and sort of infer deformation from that. And the reason for this is that basically the ground moves a lot with the groundwater levels. And so there's a strong seasonal and subseasonal behavior in both the functional and the stochastic models. And this comes what this comes down to in the end is that there's very rapid soil movement. And so we're dealing with non-stationary coherence and unwrapping errors. So to give you an idea, here's a set of ground truth measurements taken at a location in the Netherlands, a sort of representative location, where you can see sort of the vertical deformation time series over about 3 years. And you can see it's very dynamic. There's a strong seasonal component, but even subseasonally, there's large shifts. And so allow me to now guide you through a sort of simplified process of trying to get an InSAR measurement from a set of ground truth like this. So the first thing we would do is just downsample this to one measurement every 6 days, which corresponds to the Sentinel-1 overpass cycle. And then we're just going to add some noise as well. This is noise that is a function of the coherence based off of this old reference from Barber, this classic paper. And we just use a simulated coherence that sort of shows a seasonal trend with some random variations. And this varies from 0.1 to 0.65, which is sort of representative for the measurements that we're looking at. So what we get when we do this is this red time series. And the key thing here that I want to show you is that basically there are huge uplifts in the time series between individual epochs sometimes. These uplifts can be so great that the deformation can actually exceed half a cycle between the epochs, which means that it actually becomes essentially impossible for a standard unwrapping algorithm to correctly retrieve this time series. And so if we go through the sort of notions of converting this to phase, wrapping it, and then re-unwrapping it, we get something that looks like this. And we get this sort of step pattern where we have sort of highly coherent measurements in the winter, and then in the other seasons, it's very difficult to track what's going on. And so you can see there are two key points that I highlighted earlier where the unwrapping solution is no longer correct, and those end up introducing a huge systematic error into the observed product. And so this is what we want to try and deal with. So how do we tackle this? And indeed, this has to do with this link with groundwater. And so the ground truth measurements show that the shallow vertical deformation is highly correlated with changes in groundwater. The problem with that, though, is that groundwater measurements are highly localized, which is not great for InSAR. And we're not necessarily interested in modeling the groundwater perfectly or modeling the height, the soil height as a function of the groundwater, which can be very cumbersome. We're looking for a lightweight way to assess the quality of our unwrapping decisions. Did we go in the right direction, basically? And for this, we postulate that the precipitation, the temperature, and the day of year are enough to predict these changes. And so what we do is sort of use this idea of using a neural network as a classifier to predict basically if the ground moved up, down, or not significantly. And so this way we don't have to predict the entire time series. And this kind of reframes the problem from a very difficult time series prediction task to something that's relatively easy, which is just a classification problem. And so what we do is we use a recurrent neural network for this task, which is basically able to map a series of input sequences to an output label. So in this case, the output label is just a 0, 1, or 2 integer value, and that corresponds to our 3 solutions of up, down, or no significant movement. And so at the input side, we're just giving it precipitation, temperature, and the day of year to get the seasonality. And then the output looks like this. So we basically just get a big list of probabilities, probability that things went up, that they went down, or that they stayed the same. And then we apply this to our standard unwrapping solution to try and assess a level of confidence in that solution. So you can see we apply a couple of conditions for when we would like to say override this, this standard solution. And so those conditions are basically, we're only interested in applying correction to areas where there's significant movement. So the phase change is greater than a quarter cycle. The RNN needs to be confident. So we set some threshold, a very high threshold, like 99% confidence. And you can see that's in the left here, I've highlighted 2 area examples where you can see that these conditions are met. And then finally, we'd like to make sure we're not just correcting a piece of random noise, so one single outlier measurement. And we can do that by looking at the coherence and also by basically seeing the next epoch's measurement as well to see if there's a sort of random error spike or if this is a systematic thing. And so when we apply these, when we apply this logic, we get a new time series in black, this corrected solution. And you can see that the corrected solution indeed follows that original red one, which was just the downsampled plus noise, which means that we're able to correctly track the original time series again. And indeed, there are two overrides done in this case at these two problematic epochs where there's rapid uplift. So now I would like to switch gears a little bit and just talk about machine learning for ensemble behavior. So first we were just looking at individual time series. Now I'd like to quickly discuss looking at a whole scene. And so here we're trying to ask the question, sort of which regions are deforming the same way? What does that deformation look like? And what are the common factors? And so you can see on the left or on the right-hand side here, a sort of normal scene that you would expect to see in much of the Netherlands. And so what we do is apply sort of a standard DS processor, and then we cluster the output time series by their behavior. And what we mean by that is we apply this algorithm called the Tisny algorithm. And what this does is it basically looks at all the time series and it just assesses how similar they are to each other and plots them or represents them as points on a 2D output plane. And so similar time series are basically plotted very near to each other. And if the time series are not similar, then they're not plotted near to each other. So the Euclidean distance in this is not very meaningful. What you would want to look at is basically just bunches of density. So high density areas are relevant. But because if something is twice as far away from some point as some other point, that's not necessarily a meaningful piece of information in this representation here. So what I would like you to note is that of course, it's not very obvious to our eyes how we would group this, but you can see that there are some subtle variations in the density here. There's sort of areas where there's sort of patches of dense points, and there's patches where there's not very many points. And so there's indeed other algorithms that can take care of this quite easily. There's one called the DBscan algorithm. This has been around also for quite some time. And basically what you do here is you just select some random seed points and it grows clusters that spreads to the nearby points. And this allows us then to examine this ensemble behavior. So this is rather abstract. So I'd just like to show you some example of these clustered time series now. And you can see here, these are two different clusters that we see in this area. And so I'll just walk you through these figures. On the left-hand side, we have an aerial view, which just shows where exactly these DS points are and how they've been clustered together. The middle column shows all of the time series basically plotted on top of each other. And so you can see here, there is really some ensemble behavior that is captured by these algorithms. And you can see what is quite striking is how different they are. So on the top one, you see the step pattern behavior that we had mentioned previously. And on the bottom, we see the seasonal behavior that the extensometer ground truth measurements that we have seem to follow. And what I would like to point out on the right-hand side now is we have some contextual data. We know a bit more about this area, actually. We know the soil type, we know the landforms, we know the ground cover, we know the elevation, and we know the seasonal groundwater changes. And so what I would like to point out here is that these two clusters are almost identical in their makeup in this contextual data, but they show drastically different deformation behavior, and that's a bit unexpected, especially for the groundwater. You can see they're quite similar, and this has such a large impact on the deformation. We would expect this to be more similar. And so we strongly suspect that this step pattern behavior that we observe in this top cluster corresponds very much to this badly unwrapped solution that we saw earlier. And so in the next steps, I would basically like to apply this RNN correction to the unwrapping, and then we will hopefully see the cluster 2 here on the top will look a lot more like this periodic cluster on the bottom here. So just to conclude, I would like to mention 3 points. The first, that the soft soil displacement phase is highly dynamic. It's difficult or even impossible to track using the standard approach. But we can accurately predict the sign of the displacement using an RNN, and that these predictions can then be used to correct unwrapping errors in the solution. Finally, these clustering algorithms show that many regions display the same phase displacement over time, so they're following the same kind of behavior. And we strongly suspect that these groups are showing similar phase unwrapping errors. And so the next steps is we'd like to assess the applicability of the RNN model across a full scene and then apply those corrections. Thanks very much.
Thank you. I think it was a very interesting paper. Thank you for the presentation. I hope we will have many questions. And now we have to move to the next paper, though. And the next paper will be InSAR uncertainty due to phase unwrapping errors. And it's going to be presented by Zhang Junyun. And so please, Zhang, the screen is yours.
Thank you, Chair. We know, so this talk, we talked about the uncertainty of InSAR due to the phase unwrapping errors. We know that InSAR phase are wrapped and only know modular 2 pi. For DM generation and deformation mapping, we need to add an integer number of cycles to the wrapped phase to obtain the continuous relative unwrapped phase. However, wrong integer numbers of cycles can be added during this process, causing unwrapping errors. And this is usually called due to the decorrelation caused by vegetation covers, water body separation or snow covers, or by the imperfect stitching in the frame-by-frame processings. Note that unwrapping error is a processing error, not an observation noise, like tropospheric delays. So the motivation of our project is to try to better understand the behavior of the unwrapping errors and its contributions to the InSAR uncertainty budget. This is important for the uncertainty quantification of InSAR products. InSAR uncertainty model that accounts for phase unwrapping errors is also needed for the performance analysis for future SAR missions. And we can also use it to choose unwrappers, for example, for the NISAR level 2 in differiometry unwrapped products among the available choices. Here are 3 examples of unwrapping errors from the left to right. The phase unwrapping error due to the water separation between islands and due to the extreme topography causing decorrelations around this region, and also due to the incorrect phase stitchings in the frame-by-frame processings. While the first case of water separation is easy to check, the other 2 are difficult. This is because of the simple fact that we don't always know the true phase. Therefore, we cannot detect or evaluate the unwrapping errors when the phase discontinuity is not obvious. And this is a difficult task, even for manual inspections by experts. Because of this, we turned into a statistical approach with pure simulations where we know the true phase. For this purpose, we first simulate the realistic phase contributions from various sources to form a interferogram. We then unwrap this interferogram with different algorithms, such as the minimum cost flow method, and then we realize this multiple times. Then we can evaluate the unwrapping errors in terms of likelihoods at pixels, regions, or SAR image levels. For the simulations specifically, we consider 4 different components as listed here. For decorrelation noise, we use the observed coherence from C and L band data as a reference. For troposphere, we use the global atmospheric models for the stratified tropospheric delay, and use a spectral spectra from InSAR Modis or Maris dataset for the tropospheric turbulence components. And for ionosphere, here we only consider the long spatial wavelength components using the GNSS-based tech products. And we also use the estimated DM errors from InSAR time series analysis to generate the topographic residual phase. And with the limited time, I will only dive into the decorrelation noise simulation component here. So if we assume that the InSAR phase are following the circular Gaussian distribution, then the PDF of the interferometric phase can be derived as a function of spatial coherence and the number of looks, as shown as plotted on the solid lines on the right. Based on this, we can simulate the decorrelation noise. And we can see it here from the left to right, we get higher and higher coherence. Correspondingly, we get smaller and smaller phase standard deviation and less noisy decorrelation noise. However, in practice, there are several biases need to be calibrated. First, the analytical equation of the phase PDF can be imperfect. Second, the observed coherence can be biased during the coherence estimation process due to the limited sample size and the complex phase patterns. While the last one has been already addressed, the first two are not. So here we just follow the principle of single variable experiments by model the impact of the first source by suppressing the other two. In this case, we use a very large sample size to suppress the impact of the limited sample size, and we use a simple zero mean decorrelation noise to suppress the impact of the complex phase patterns. And here on the plot, where the x-axis are the true coherence as input, and the y-axis are the estimated coherence, the output from the simulations. So we know that ideally they should be identical to each other, following the diagonal lines here, but they're not. And we can see that this bias is a function of both the input coherence and the number of looks. But luckily, this bias can be easily modeled as a polynomial functions. And after modeling that, we can remove that, and now the simulation part is working as expected. Following the same philosophy, we can do the same thing for the impact of the limited sample size, where we model the bias using a spline function instead. And we can similarly correct for it too. So for this part of the simulation, we can validate it by comparing the input observed coherence with the coherence estimated from the overall simulations, where all the phase components are considered. And here are the results, where we consider several different scenarios of coherence. On the left columns are the histogram of both the input observed coherence and the simulated coherence. And on the right column is showing the same thing, but in a scatter plot, where the x-axis are observed coherence and the y-axis are simulated coherence. And we can see that from different rows, the overall coherence level is decreasing from high coherence to moderate to very low coherence. And we can see that in all these scenarios, the simulation is working as expected, which means the simulation of decorrelation noise and the coherence estimation in our workflow is working as expected as well. So with these simulation tools ready, we can sum up the whole thing. We use the observed interferograms as input reference, where we can simulate the phase contributions from various sources, including the decorrelation noise on the left, the stratified troposphere, the tropospheric turbulence, only the ramp part from atmosphere, and the topographic residual phase. And we can add all of them together to form the overall simulated interferograms. And we hope and we believe that these simulated interferograms are in a similar noise level as the input phase. So with the tools ready, we can apply it to real interferograms. Here we show one interferogram of Sentinel-1. It has a temporal baseline of 24 days. And from the left to right are the simulated spatial coherence, the wrapped phase as input for unwrapping, the integer ambiguity that the unwrapper is supposed to resolve, and the unwrapping result. Here we show the unwrapping result as the unwrapping errors, which is literally the difference between the truth where we know and the unwrapping result. So we can see here the majority of the areas is green, which is unwrapping error free, and all the blue, dark blue, and orange regions are having unwrapping errors. And on the far right is a map of kinetic components, which is a byproduct from SNAFU. One kinetic component is defined as a group of pixels that are believed to be correctly erupted locally. And this parameter is turns to be a very valuable parameter for the evaluation of RPM results too. Here shows another example with a longer temporal baselines, which also give us an overall relatively lower spatial coherence and a smaller spatial and a smaller spatial coverage of the kinetic components. And we also notice that the RPM errors on these interferograms is also slightly higher, which is expected. So we can apply this. So we can repeat this process to one interferogram a lot of times and then get some first-hand statistics. So this figure shows for each pixel the occurrence probability of RPM errors among the 100 realizations. So here the yellow region showing RPM error free, which is the reference kinetic component we're choosing, while the dark blue regions are having RPM errors all the time, which is not chosen which is chosen as the background value or no data value in the kinetic components part. We can show the similar thing where here on the right shows for each pixel the maximum magnitude of the RPM errors among the 100 realizations. And we found that when there is no significant phase gradients from ground deformation or atmosphere, like the atmospheric strikes, then the magnitude of the RPM errors is bounded within 4 cycles or 8 pi. Another statistics is showing that for each pixel, the number of times is chosen as kinetic components. And we can see that basically this yellow region are chosen as kinetic component all the time, while the dark blue are not chosen as kinetic components all the time. So we can see that there's a relatively sharp boundaries, and the spatial extent of the kinetic components are very stable among these 100 realizations. We can see that also through the histogram here. Note that this is in a log scale. And even in this scale, we have a very strong single peak, which means that the spatial coverage of the kinetic components are still very stable among the different realizations. So this raises up a question that can we use the kinetic component as the basic unit to evaluate the RPM errors? So to answer this question, we are checking the false positive rate. What that means? That means we're checking the rate of how many percentage when there are 2 pixels, if they are in the same kinetic components, they are having different RPM errors, such as this one marked here, where they're having the same kinetic component value, but having different RPM errors. And we found out that actually this rate is really low. It's less than 0.1%. So answer to the question is yes, we think we can use it as the basic unit. So with this, we can actually just use all the statistics from the multiple realizations to quantify the RPM errors, to quantify the uncertainty of the RPM errors. One choice is simply using the mean absolute magnitude of the errors among different realizations. Here is one example, where for one interferogram, we have the coherence, we have the erupt phase as usual, and on the right are in the unit of kinetic components, the mean magnitude of RPM errors. And we can see that still on this region is RPM error free because we choose the reference point here. On the regions in the far range, they are having RPM errors, but are still bounded within 5 radians. So we can apply this now to a larger region where we choose the whole California using the array products. And on the left are the spatial coherence map. We process this big region block by block, and within each block is chosen a local reference point as indicated by the red dots here. And on the middle column, middle and the right column showing for each pixel the occurrence of possibility of RPM errors and the mean magnitude of RPM errors. And we can find that clearly the RPM errors are clearly correlated with the spatial coherence. And in the low coherence region, such as here in the mountain range, and here, when the coherence is low, the possibility of error errors is pretty high. And when the coherence is high, the error error is usually really low, unless it's separated by the correlation noise, such as this island here due to the water separation, or this corner here due to the separation of the mountain range in the frame in the block by block processing. And we are also trying to model the uncertainty of errors as in the SAR image level as a function of radar frequencies, the correlations of topography. And one working hypothesis is that with longer distance between kinetic components, there comes larger errors. And with the current statistics, it shows that this seems reasonable. So in summary, we developed a tool for realistic phase simulations and a method to quantify the errors in terms of the occurrence probability and the magnitudes. And we find that the error is bounded within 4 cycles when there's no significant phase gradients. And the kinetic components are a reliable indicators for potential errors. Future work will work more on the uncertainty quantification in the SAR-SIN level and propagate the uncertainty from interferograms to the time series and velocities. Thank you.
Thank you. Thank you. Your was a very interesting paper, very interesting for applications. So we look now to the question and answer session, and I hope you have many questions. Let's give some time to the audience to propose questions to you too, because now we have very many questions for Homa, for Philip, for UGA. And my opinion is that we start with those who had a little smaller number of questions, so they have some more time, so they are not squeezed at the end. So my first, I would start with UGA. I found one question for you. In rapidly decorrelating areas, can we effectively mitigate the fading bias with your method? And then after you answer this question, it will be time for Philip, who has many, and Homa, who has very many. So let's go ahead, or the opposite order, depending on how many recent questions have arrived. So please, Juji, you start.
Okay, thank you for the question. So we use long span closure phase, sequential cumulative closure phase to estimate the bias. So no matter how decorrelated it is, the bias information is contained in the closure phase. It is true that we may experience some difficulties in unwrapping the closure phases to get the actual bias, but I think the most difficult problem is actually getting the original time series, either using SBAS or full bandwidth SQUEEZAR. We may have unwrapping error problems or some other errors instead of bias. And yes, that is all.
Thank you. Thank you. So now I think it's the turn of it's the turn of Homa. Okay, so you have many questions, and then Philip has even more. So Homa, do you know which ones are your questions? Do you want me to recollect them? I can tell you a few. Are there any safe DS which are not PS? What processing would you suggest for areas with strong temporal decorrelation? Any assumption on the Tibet plateau? You had the same number of let's check, pixels in your SBAS 10 and EMI. Why do you expect the number of pixels to be reduced? Which machine learning did you use? You may consider answering some less complicated question here in the chat. So go ahead, Homa.
Thank you, Professor Roca. So I start from the safe and the prone DSs. So I believe there are safe.
Excuse me, Homa. Please repeat the question first to be sure that you understood it quite nicely, so that everybody can understand the question you are answering. So take your time, repeat the question, and then give the answer.
Sure. The first question: are there any safe DS which are not PSs? I believe there are. So the safe DSs that I tried to detect with the machine learning algorithm, they were still the result of multi-looking, and they were not single look PSs. I expect to see the safe DSs over homogeneous areas where there is no soil moisture, no vegetation, and mostly, for example, so there should be a very high correlation with the land cover. And I expect, for example, over rock areas to see such safe signals as we see over Mount Etna, for example, over Sicily, Italy. We see this region of safe DSs. So this is where my expectation comes from. So I believe there are safe DSs as well. And this can be revealed by the residual phase screens. The second question, what processing, if not SBUS, would you suggest for areas with a strong temporal decorrelation? It really depends on the definition of a strong temporal decorrelation, because there are strong temporal decorrelations where we still see a very weak but still long-term coherence. Over such areas, phase linking approaches such as SQUISAR, EMI, etc., they can still perform very well. If we have very strong decorrelation, in the extreme scenario, one could imagine water bodies, or for example, very dense vegetation such as forests, for example. The question is, if we have such extreme decorrelation, can we at all rely on interferometric, and can we at all retrieve a safe and reliable deformation signal? And the answer, I think, needs to a little bit further investigation. If SBUS is the way to go, then we have to really scrutinize SBUS in such regions. But maybe with the calibration approaches that was proposed today in this meeting, and there is another calibration approach by the COME, which is actually presented in FRINGE as a poster. Such calibration approaches, after long-term scrutiny, they could also provide an answer. The third question, any assumptions on the Tibet plateau results? Well, one assumption is soil moisture. We have not investigated, or better said, I have not further investigated the Tibetan plateau for the soil moisture analysis, but one assumption is soil moisture, because the sign of the phase component is actually very well explained by the soil moisture model of my colleague. Regarding the seasonality of the fading signal, there's a weak seasonality that might be associated with soil moisture, but the signal that the seasonality actually causes is of much lower magnitude as compared to the vegetation growth, at least over Sicily, Italy. The next question, you had the same number of pixels in your SBUS 510 and EMI, while we expect that the number of pixels be decreased when using the longer term interferograms. So how much the use of EMI while decrease the number of pixels compared to example SBUS 5? So I was trying to keep everything completely identical in between the in my comparisons in different processing schemes. That is why the multi-looking factor was completely the same from EMI to SBUS 5 and 10. I would argue that the multi-looking factor would have in this case an effect on the dispersion. But when it comes to systematic signal, if there is a systematic signal, it will be revealed. So I don't believe that the change in the multi-looking factor from SBUS 5 to EMI would have any, probably any ramification for the result of the comparison, let's say. The next question, which machine learning method did you use to detect safe versus prone DS? Was the bias of individual DS considered? So basically the features that was the input to the machine learning approach was the residual phase screens. What I was using at the time was a clustering method, simply because I was handling the case as an unsupervised machine learning approach, so without providing any labels. And what I see with my evaluation is that based on this clustering approach, what I see is that the result is very much in line with what I see from the error propagation and the velocity error that are predicted as well as observed. So yes, that was the answer there. Was the bias of individual DS considered? This part I'm not very clear on the question, in fact. So the bias of individual DSs were actually manifesting themselves in the residual phase screens, which were the features to the machine learning algorithm. So I believe the answer is yes, but if I did not get the question correctly, please contact me later. I guess that was all for my questions.
Thank you. Thank you. Now is the turn of Philip. Please take 7 minutes because we have questions for Zhang and Yuyun. So we will need to devote some time, a couple of minutes at the end for them. So go.
Sure. I'm seeing two questions for me. So the first is the clustering of time series based on unwrapped or wrapped phase histories or on complex numbers? And indeed, the clustering is based on the unwrapped time series. So we haven't looked at the wrapped phases yet, which is something we'd like to do, or indeed the full complex image. So we haven't looked at the amplitudes at all either. So so far, we're just looking at the unwrapped time series, which is part of our plan was to see if we can detect the systematic effects of phase unwrapping errors. So that was part of the goal to pick up on that. But indeed, this is also something we'd like to look into. And the next is, I mentioned a classification, a supervised approach with an RNN. How do you prepare your, I think the question got cut off, but I think I understand. How do you prepare the training data, labels? So we had this extensometer data, which is basically a sort of geophysical device that's planted in the ground and it's measuring the surface level. And what I do is I basically take the sign change between InSAR measurement epochs. So I have sort of daily values, but we're actually taking the label based off of the sign change between the InSAR observations. So that's a change over 6 days, not a daily or an hourly change. And now I see another question's popped up. I'm wondering how
I have another question for you.
Yeah.
And this is in the first, actually, the previous question was with RNN, how do you prepare your labeled training set and how large it is? And this you answered. And then the next question is in the first part of your presentation, which was a list of features used in the RNN modeling. Did you also use the amplitude time series?
Yeah, so our features that we use are the precipitation data that we have from the Dutch Meteorological Society, the temperature levels also from them, and the day of year. So that's 3 features. So we're just keeping it simple. We're not looking at the InSAR amplitudes yet.
More questions are raining. So how robust is a 2D search space classification result? Would other algorithms change the outcomes and how would this affect the analysis? One. And then there is another. If there is a wrapping errors, won't those errors affect clustering? So
Yes, yeah. So I'll address the second one first. So if there's unwrapping errors, these will affect the clustering. And indeed, like I said, that's kind of the point. Like we want to find and cluster all the areas that contain unwrapping errors, and indeed the same unwrapping errors that are occurring at the same points in time. That's actually a key goal that we want to have. Secondly, how robust is the 2D search? You can output this into a 3D plane. I'm not really convinced that that's going to change much. I think, as you saw, the clusters themselves looked pretty good. They're good enough for the application that we're using them for.
So thank you. We are done with Philip. So now let's go back to Zhang. Main reason of the wrapping errors is the deformation behavior. Are you reading that question, Zhang? So go ahead and answer.
Okay. So the question is, my method did not require deformation assumptions, and how? The answer is we could definitely include the deformation patterns and the gradients if we have the models, and we definitely will do that in the later. And then the method which we present is definitely insensitive to that and can include it and work out of the box for it. And so yeah, so the short answer is yes. In the future, we will definitely include that.
So, Yunyun, are you reading the question? Fading signals proposed by HOMA will be an effect on wrapping errors. So could you give an answer to that?
Yeah. The fading signal, as presented by HOMA and Yuji today, is in single interference. It's actually relatively small, and the RP errors we are seeing is always the integer number of 2 pi's, which is really large. So we don't think that the fading signal will actually have a strong impact on the RP errors. And even if there is, the method of where we do the statistics and then with simulations, we think we can still insensitive to this effect or the multi-look phase.
Thank you, thank you. I think we made it. So we answered the questions, and I think this session was a real success because we were able to hear very interesting talks and to have an interesting question and answer part. So now I'm happy to leave the lecture to Howard. I hope he'll be here. And so to start the next session on advances of InSAR theory and methodological innovation 2. Go ahead. Thank you.